So let's begin on 1G and 2G networks. And right now we are, you already know what 1G and 2G are, first generation and second generation cellular networks, right? Right now we are in 3G. So 1G and 2G is more of a historical interest. So we are going to go a little bit faster on these to show you what these were, and then we go to 3G and 4G. So we'll talk about the cellular architecture in general. We have talked some about it already when we talked about WiMAX, but we'll have a little bit more detail. Then we'll talk about a historical system, again AMPS, another one CDPD, and then we introduce the generations and we talk about GSM. GSM is actually the most common system which is in use today. So we'll take a little bit more detail on that one. And CDMA1, which is another 2G system, we'll talk a little bit about that. So GSM is where most of this time will be spent in this lecture. So the great idea that somebody got in AT&T was that we can reuse frequency if we limit transmission to a certain area called cell. This happened about 30 or 40 years ago. And so now we have the whole world is divided into cells. And when you divide the cells, you first decide a cluster size, where cluster size is where basically how many cells in the cluster will have different frequency, and then as soon as you get out of the cluster, we reuse the same frequency. So if you have a cluster size of 4, you will have 4 different frequency bands that you will use in that cluster, and as soon as you get out of that cluster, you will use the same 4 frequency band again. So the size could be 4, 7, 19, and in case of 7, it is basically a hexagonal thing where you have a central cell which is hexagon, and then 6 cells which are around it, right? So you will get a cluster of 7. Similarly, cluster of 19 you get if you take this hexagon, then you take the 6 cells around it, and then you take that is 7, then you take 12 more cells in the second layer around it. So you make basically a cluster whose radius is 2 cells in some sense, okay? In general, the cluster size has to be I square plus j square plus I times j, where I and j are any integers, 0 through 1, 0, 1, 2, 3, 4, 5. So you put any number 0, 1, 2, 3, 5 for I and j, and whatever n you get, that is the possible size of the cluster size. Because these things are repeating, so you could not have cluster size of 5, for example, because 5 does not fall into this I square plus j square times plus ij times formula. And it turns out if you know the cluster size, then you can, so these are the possible cluster size values. You could have cluster size of 1, which means that every cell has the same frequency. Cluster size of 3 means you will have 3 subbands, 4 subbands, 7, and so on and so forth. So that is straightforward then. Now if you have a cell whose radius is r, and somehow you include, you reuse that frequency after a certain number of cells. Let's say the cell that is using the same frequency is capital D away, right? And because there is an overlap, the little d is the distance between the centers of the adjacent cells. So that determines the capital R, and little d determine the overlap. And so if there is no overlap, then basically capital and little d would be 2r, but generally there is an overlap. So if you know these 3 numbers, little d, capital D, and r, then you can basically they are related in some sense, and the relationship is that if your cluster size is n, then square root of 3n is d upon r, or square root of n is d upon d. Now geometrical, this is simple geometrical relationship which can be easily be proven, although we will not go into that. But basically, since these things are hexagonal generally, the d, and you can take an hexagon and and use the cosine and tangent and all those functions, and you can figure out that little d is r times the square root of 3. Okay. To make it an hexagon, and therefore these things are valid is because d upon r is square root of 3n and d upon d is square root of n, and so one of the things one could do is, if they have a certain area to cover, and then they can decide, if they use the cell size radius of little r, how many cells they will need, and what would be the repetition pattern, and so on. Okay. Here is an example of that. Let's say your cell radius is 1 kilometer and reuse factor is 12. So this is the cluster size. So how far away the same frequency will be used? So capital D upon R is equal to square root of 3n, and the square root of 3 times 12 times 1 kilometer is 6 kilometer. So basically 6 kilometers away the same frequency will be used. Okay? Yeah.
I'm wondering, how are these cells used? Like, what are they exactly physically?
What are they exactly physically?
Yeah, like if I want to touch a cell, what is it exactly?
So basically what you will see is, in the center of the cell, a tower. Is that what you're asking? And so each of these cells has a tower in the center, and that tower is broadcasting some wireless radio wave, and if the cluster size is 7, then this one would be broadcasting the same thing as this one here, I mean just outside the cluster. Is that the question? Is that the answer?
So that means that the other cells that are not part of the cluster are sending in a separate.
Okay, so basically inside a cluster you don't use the same frequency again. So each band is unique inside the cluster. As soon as you get out of the cluster, you are reusing the same frequency. So the advantage of knowing that it is 6 kilometer is the cluster radius is that your transmission should be powered such that it has very little effect after 6 kilometer, right? Because after 6 kilometer we are going to use the same frequency. So it's like, let's say we use channel 2. So we are transmitting on channel 2, and you can imagine television, we are transmitting television on channel 2. When can we use the same channel 2 and transmit some other program, right? So it has to be 6 kilometer away by this design. So how much power is required so that we don't overflow after 6 kilometer? So all that design is done that way. Okay? Now the way the cellular system is structured inside is shown in this slide, and this slide goes along with the next slide, which you can read. Basically, first thing we have is the cell phone. Cell phone is called mobile equipment. Inside the cell phone there is a card which identifies the user, and so this is called subscriber identity module, SIM. So, and this particular architecture clearly relates to GSM, where there is a SIM. In many of the other systems, such as CDMA systems that you might have. If you have a Sprint phone, for example, here in the United States, there is no SIM because that is hard-coded. But in GSM in particular and other systems, there is a SIM card, and the advantage of SIM card is that you can take that card belongs to you, you can put it in any phone, and that phone becomes yours. Right? The number and everything else is transferred immediately to that other phone, and so that's very convenient. You can switch the phone in an instant. And in other states it's not very popular, but here if you have AT&T service and your phone goes bad, you can just take your wife's phone or your husband's phone or anything and then put your SIM in it, and it becomes your phone. Okay, so it's very easy to interchange the equipment as long as you change the SIM. So SIM is the thing that you subscribe for, subscriber identity module. So that is what user is. Everything related to the user, including the phone number, is in the SIM. And the SIM also includes, for example, your directory, phone directory. So if you change the SIM, all your new numbers are already in the new phone, your friends' numbers and everything else. Alright, so that is two modules. Then on the other side, we have what we call BTS, base transceiver station, and that is actually the radio part of the tower. There might be many base transceiver stations which are controlled by a single intelligent system called BSC, base station controller. So the radio is here, which is mostly analog, and the digital part is here, which is BSC. This is where the basically the thing that controls programmable and things like that are all here. This is mostly analog. BTS is mostly analog. BSC is mostly digital, right? So that is the one. There are multiple BSCs which are connected via wired network to a MSC, which is the Mobile Services Switching Center. And MSC is like a room. So this is like a tower on the mountain. This is like a head office or something. And in the MSC, they have lots of other things related to users. And so there are many databases which are shown here. 4 databases are shown here. First database is home location register. This is for all the people who belong to that area. So if you are in St. Louis and you subscribe to AT&T St. Louis, your information will be in St. Louis home location register, HLR. Visitor location register, everybody who is not from St. Louis but visiting St. Louis, they will be in visitor location register, right? Because they are still using the cell phone. Equipment identity register is basically every equipment has a number. If when a cell phone gets stolen, we can figure out that this is a stolen cell phone because the equipment identity is registered. So that is information is here. And so if we find somebody using a cell phone whose identity is is written as a stolen here, then we will just know that this is being misused. Or if we find it's okay, then we leave it alone, right? Authentication register is just making sure that the right people are using the equipment and right subscriber is using the equipment. The subscriber is still authorized. Subscriber has paid the bills and so on and so forth, right? So that is authentication. PSTN is the public telephone network, and so this is packet switched telephone network. So this is your the normal telephone network. Huh? Public switch telephone network, I said, yeah. Public switch telephone network. And so this is the wired network. Basically, so BSC onwards, it is all wired. And MSC is the main brain. Then little bit brain is in the BSC, and these things are simple analog systems which just transmit the radio waves. Yeah.
So there are multiple MSSCs for the switching centers?
Yeah, MSCs are, there might be, there are many of them. So here's the thing. Each of these is called a cell. right? Each BTS is a cell, right? So there are multiple cells, and then so for multiple cells there is one MSC, and then there are multiple MSCs in a country or a state or something like that.
I mean, would there be like one MSC for the Midwest or one MSC for St. Louis?
Okay, so there would be a lot more in Midwest. There would be one more like multiple. There might be even multiple MSCs in St. Louis, but so there are only so many users they can cover, and depending upon the density of the users, they will keep certain number, so few thousand. Yeah.
What are the location registers and visitor location registers? Are those servers, databases? What are they exactly?
So these are databases, and what they are is that if your cell phone number, whatever number it is would be in the HLR or VLR. If it is not found, then basically we have to find out where your home location is, contact them, and find out whether this person is still paid the bill and can we connect him if you're roaming, right? And then your name will appear in the VLR, and whenever somebody calls you, then we can connect you.
And is the mobile service switching center, is that that's something that occurs in actual hardware, or is it something that is completely wireless? Like, is the signal converted to like a line?
Okay, so this is all wired network. From here on, actually everything here is wired. The only wireless link is this one here,
Oh, okay.
right? Although having said that, this is wired, but wired also includes wireless. I mean, if you are connecting two switching centers in the mountain, you might not put a wire, you might put a wireless link, but that is just for convenience. So these things are all wired here. And so here the thing, the name mobile switching center, actually we will discuss a little bit more later on, but the key is that whenever you switch a tower, the decision is made here. So when you are going from here to there, this one tells it that move it from this BTS to that BTS, and so on and so forth. So all the information about the signal strength, etc., comes here, and from there it goes there, and this one makes the decision as to what to do. So all the handover, etc., decision, all the decisions are made here. MSC. All right. So this is called mobile station, this is called base station, and this is called network. All right. These three words on the bottom. So I think we have covered everything. BSC, BTS, and so basically here the thing about the handoff is that BSC BSC manages the handoff between the BTSs, and MSC handles the changeover between the BSCs. Switch is called between the BSCs. So this is a hierarchy. If you stay in the same BSC, then you will basically BSC can decide. All right. And then mobile switching center does most of the other things, such as registration, location, authentication, and so on and so forth. More about HLR, visitor location register. They contain routing and roaming. Equipment identity register, we talked about that, and we talked about IMI. So we have talked all about these in this slide, also all the numbers. So this system of MSC, BSC, BTS, etc., this is common among all the different kinds of things. Some of them have used SIM as a separate module. Some of them have made SIM as the part of the mobile equipment, right? So that's why not every phone has a SIM. How many people have a phone with a SIM card? 3, right? 4, right? So at least you know what a SIM card looks like. Like some of you have seen, you can take a SIM card from one phone and put it into another phone, right? So, all right. So the very first system cell system that was deployed is called AMPS. Now again, AMPS is more for today for historical reasons, and you need to know the word AMP. And so I have put a single slide on this one. Basically, this is the first generation analog system. And by the way, all the first generation systems were analog. So that is the thing which distinguishes 1G. 1G is all analog. What is analog? The wireless part. So whatever is going from the tower to this phone is an analog wave rather than a digital wave. It's not zeros and ones going, it's a wave going. Huh? No, that is just the dumbest thing you could do. I mean, that is how much knowledge we had when this was done. I mean, here's the thing, everything was analog before. We are moving to digital now. So this was analog. Right? It doesn't save anything, it's just that we didn't know better. So it is first generation analog, and this was obviously in North America, and this also in some sense one of the first ones worldwide. So this uses 225 megahertz band. These are the 25 megahertz bands, 869 to 894, exactly 25, and 824 to 849. So this is for the down and this is for the up. Everybody knows what is down mean? Down is from where to where? Yeah, tower to the handset is down. Tower is here in the mountain, handset is on the ground. So that is down. And the handset to the tower, it says right here actually, BS to mobile is down, and the mobile to base station is up. And so there are two different bands. Each market, two operators are accommodated. So we get 25 megahertz, we give 50 megahertz to each operator, and each area will have at least two. So we need 100 megahertz per city. Actually, not for this is not a city. This is actually, they call it area, which is defined. There are 400 and some areas in the United States. They'll come up later. So there are two operators are allowed. Each operator is allowed only 12.5 megahertz in each direction, and the channels are spaced 30 kilohertz apart. So each user gets 30 kilohertz, and therefore you can have 416 channels per operator. Out of them, 21 are used for control and paging and access, and 395 for traffic. So 395 people can talk at the same time. So this is what is also called frequency division multiple access, FDMA. So we take the frequency 12.5 megahertz, divide that into 30 kilohertz channel, and everybody gets 30 kilohertz, and they keep it for the whole time when they are using it. And obviously if you are not using it, then you are just connected to the control channel and not to the traffic channel. So 395 people are actively talking, right? Not just on. More than that could be on, right? Each channel uses two traffic channels, forward and reverse, and the forward and reverse are exactly 45 megahertz apart. So if I give you 869 here, I will give you 824 here, and they are exactly 45 megahertz apart. Right? If I give you 825 in the up, then I will give you 825 plus 45 in the down.
So that means that one tower could support about 400 people?
One what?
Is that what this means?
Yeah, 395 number of people could be actively talking on 12.5 megahertz.
But that was like for one tower, right? For one cell.
That is for one tower, yeah. And the control channels are, now here is interesting, control channels are 10 kilobits digital channels. Okay, so they are not analog. And so what goes on a control channel is commands, like turn on this cell phone or turn off this cell phone, or you are connected or move or whatever, right? So all those commands are digital commands. They go on the control channels, and they are 10 kilobits and they are digital. Traffic channels are analog and they use frequency modulation. And So anyway, so this is the simplest system that could be done in those days, right? Obviously, we don't use amps anymore. After amps, another historical thing that happened was CDPD. CDPD is cellular digital packet data. So if you wanted to do data in that amps kind of system, then they said, okay, what we could do is we could let you use data whenever nobody is using the channel. And so they designed a system which will automatically hop from channel to channel to channel depending upon when somebody is using it. So you are using this channel, this dot 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 is data. As soon as somebody started using that, you hop onto the next channel. As soon as somebody started using that, you hop onto the next channel. As soon as somebody starts doing that, you hop on the next channel. So you just keep moving from channel to channel just for data. And this system was called CDPD. Again, we don't use any such system anymore. Okay. So now that we understand enough about this, let's talk about the generations. So the first generation is, the key thing about the first generation is that it is analog. The second generation is digital. So if somebody asks you what is the difference between 1G and 2G, the main difference is 1G was all analog, 2G was all digital. If anything is analog, that is 1G. And 1G has basically is analog, and therefore if you need to do any data, the way you do data is by using a modem. Modem is modulator demodulator, right? So what it will do is you give it zeros and ones on one side, the modem will make a continuous wave out of it, and it will look like a sound wave, and it will send it over that analog channel. At the other end, another modem will convert that back into digital. So you will be able to get maximum of 9.6 kilobit per second using 30 kilohertz. 30 kilohertz today we can get out of 30 kilohertz almost like 6 bits per hertz. We can get 180 kilobits. But in those days you could get only 9.6 kilobits. Now 2G makes it digital. So by the way, 1G is right here. So 1G is mostly voice. I mean, you can do data by modem, but again that data is really converted into voice. So, and it is all FDMA, frequency division multiple access, and two systems are AMPS and TAX. AMPS was used in the United States, and TACS and TAX was used in Europe, and the acronym for TAX is listed right here. Total Access Communication System, TACS. Now 2G is all digital, right? So because it is digital, we could do some data, although the data is not as high speed as we will call it today, high speed data. So we call it low speed data, and then it also be switched here from FDMA to TDMA and CDMA. TDMA is, what is it? Time division multiple access, and CDMA is code division multiple access. So there are two kinds of 2G systems. Alright. In time division we have two systems. One is called International Standard 54, IS54, DAMPS, which is digital amps, and the other one is GSM. And now GSM is what was used mostly in Europe, and DAMPS was mostly in the United States. Alright. Then there was a modification of that, and it was called IS136, and GSM actually runs on many different frequencies, and depending upon the frequencies it could be 1800 megahertz or 1900 megahertz, or actually I think there is also a 900 megahertz. So anyway, so there are several GSM varieties depending upon just upon the band. This NA means North American GSM. And then CDMA is code division multiple access and also known as IS 95, International Standard 95.
They have CDMA in Europe, because I remember you said GSM was wide in Europe.
Yeah. Okay, so here's the story. Basically, if there is, it is very rare. Rest of the world is all GSM as far as I know. Most of the world is GSM. North America is Mexico, US and Canada. Right? These are AT&T. So that AT&T was one company which was controlling all these three countries, right? So North American standards are always different than the rest of the world. So when we say the rest of the world is GSM, is United States GSM? Yes, there is some GSM in the United States too, right? But most of it is not GSM. Whereas if you go outside, you go to China, you go to India, you go to any other place. Now, having said that, there are exceptions. If you go to Korea, you will find CDMA. If you go to India, you will find CDMA too, but very few operators. Right? In general, most prevalent system right now is GSM.
Why hasn't it been adopted by AT&T as well?
Okay, so this is what happened actually. This is true not only of all communication technology, whether it is visual, television, whether it is phone. We invent. United States invents. So they, by the time it goes to other places, we already have more knowledge. So they adapt the better system. And we are stuck with the old one. So starting with electricity. Electricity here is 60 hertz, 120 volt. Rest of the world is 50 hertz, 240 volts. All right? 240 volt means less current, thinner wires, and lots of other advantages. Okay? And so why did they adapt? Why can't we go up to 50 hertz? Because we are 60 hertz. So television, we have NTSC, right? They have PAL, and in some sense, you can. We have 30 cycles per second, 30 frames per second. They have 25 frames per second. Why? Because their electricity is 50 hertz versus 60 hertz. So there is a historical reason for us, and we have to pay a price also for being first. So we cannot always be the best. It's like this. I mean, basically, Microsoft cannot always be the best because now they have something existing. If you have something existing, then you have to just slowly adopt the new stuff. If you're a new company, you can just adopt the new stuff, right? So this is the thing we have. Does that explain everything? So our system is different because it came here first. And then it is not the best because by the time it goes somewhere else, they know better system. So anyway, so GSM has DS 1800, 1900, and so when you get a GSM phone, actually you do have to get a phone which is either single band or 3 band or 4 bands, because the advantage of a GSM phone is it works in every country, but it will work only if that country has that frequency. Every country has a different frequency. So generally when we buy a GSM phone for international use, we buy 4 band or 3 band, tri-band or 4 band kind of phone. Single band may not work in outside the country. All right. So amps and deamps, basically they were basically compatible because so that whatever was done in amps could be used in deamps. But this is the real TDMA system, 2G system, and GSM and so on and so forth. So we now understand 2G. I think we covered everything on this slide. Yeah. So there is another word which is used called PCS. So basically we started in the United States something called personal communication service, and the personal meant user specific versus location specific. So the thing is, so additional bands or frequency band was released for PCS services, which were basically related to the user rather than to the phone. And so, so basically FCC gave some special spectrum for PCS, Although today there is very little difference between PCS and cell phone service. I mean, everything is, so it's kind of difficult. But basically there is a special spectrum for it. So there is a unlicensed PCS, and then there are A, B, C, D, E, F, G, H. There are some spectrum. So this is PCS is different mostly in terms of spectrum, not so much in terms of services now. And one of the system that we use in the United States is called CDMA1. Okay, and this is the wave of late 80s and early 90s. That is when the CDMA was really, I shouldn't say invented, was really put into practice. At that time, the common knowledge or common wisdom was that the best way to do multiple access is CDMA. Every system at that time was, so we already had 2G, which was CDMA1, but the whole third generation is CDMA. Everything, all worldwide, third generation is CDMA. And so CDMA was the best thing. Now the fourth generation is going for OFDMA. So after 10 years, we now have given up on CDMA and we are going to OFDMA. But so basically, this was the first CDMA. That's why it's called CDMA1. And so this is basically also known as IS-95A. Then there is IS-95B, which is CDMA2, and then there is a CDMA 2000, where the year 2000, the number 2000 reflects the year. That is 3G. Right? So here, with CDMA, on a single carrier, you could have 20 to 40 calls. So basically what we are doing is, we had those 30 kilohertz channel, remember? 30 kilohertz to each user in first generation, and we could only have 300 users at the same time talking. Now, as the cell phone became popular, we needed more and more. So what we said was, we will do TDMA. TDMA means we still have FDMA, but each carrier is time division multiple access. So you get for 1 millisecond, you get for the next millisecond, you get for the next millisecond, and so on. So we do TDMA for each carrier. Right? So now we can support many users on one carrier, but the number was small. In TDMA, the number would be more like 8 users per carrier. With CDMA, you could do 3 times as many, 22 to 40. Right? And we already know what is CDMA, and CDMA is done by spreading code basically. So you have, everybody has a different code. So that is multiple chips per bit, if you remember. And so you would get one code when you are supposed to when you want to transmit a 1, you transmit instead of 1, you transmit some code like 1001. So depending upon how many bits we use, we can have that many more users. Although if you have too many users, they will not get enough bandwidth, and so the rate would be very low. So use different spreading code. And neighboring cells can use the same frequency spectrum, but different codes. So you could also define, you could also use the same frequency in the next cell as long as you use different codes. But CDMA has one problem, that the power control has to be very precise. What that means is that the users which are very close to the tower, they cannot transmit at a very high power. Because if they transmit at a very high power, the user who is very far away will not be heard. Right? So we have to tell the user who is close to us, saying that please reduce your power to 1/2, or reduce your power to 1/4. Right? So there is a continuous power control. As the user moves, their power is changed. Right? Because they are transmitting at the same time, right? In TDMA, that is not necessary, because in TDMA, only one person transmits at a time. In CDMA, they're all transmitting at the same time, so we have to have precise power control. And by the way, one company which mastered all this art is, I forget the name. What is the name of the company that does CDMA? Qualcomm. So Qualcomm basically has lots of patents on CDMA. And they dominated the world basically during the CDMA period. every cell phone company, operator and equipment manufacturer have to pay royalty to Qualcomm for CDMA. Alright, so it can serve more users than TDMA or GSM, and data users are limited to 4.8 to 14 kilobits, and CDMA2 offers the extension to up to 115 kilobits, and Verizon and Sprint are CDMA1 networks in the United States, right? Those are the two CDMA guys. GSM is Global System for Mobile Communication. Actually, it is Group Special Mobile. This is French, I suppose. And it was developed by CEPT, which is Conference of European Post and Telecom. So this is European Standards Organization. Basically it was designed so that it has good speech quality. It has ISDN compatibility. What is ISDN? ISDN is Integrated System Digital Network. Integrated, forget S for integrated, whatever, ISDN, digital network. So basically what happened was, in the wired side, we started getting digital too, not only the wireless. And the first digital service for home was called ISDN. Integrated Services Digital Network. So basically, so that was the 192 kilobits DSL, you can call it now, but it was not really DSL. But that is the kind of service you would get. And so this is compatible with that. And fraud secure. And so that this is basically by the time, and I could go into these stories, but there are lots of stories about how the cell phone was very insecure, at least in first generation, where anybody can listen to your calls, anybody can basically make calls using your number or phone or whatever it is. So that was all eliminated by GSM. Completed in 1990, service began in 92, 900 megahertz in Europe, 1800 in UK, and 1800 in Russia. So 1900 must be must be North America. I think so. So we already see 900, 1800, and 1900. There are 3 bands in 3 different parts of the world. Yep, right here. So FCC allocated 1900. So if you want to use in North America, you have to use 1900, North American GSM. So if you want to use your GSM phone from here in Europe, you really need a dual band phone. Dual band means that it has to work on 1800 and 1900. Sorry, 900 and 1900. For example, in India it is 1800. So if we need to make it work in India, we take it 1800. And basically, generally, you get a three band phone, so we can use anywhere in the world. Voice Stream, PowerTel, Bell South Mobility use GSM, right? And 200 GSM networks in 100 countries worldwide. I think this number must be old. So now, and basically, there's a lot of GSM everywhere. So how does this work? Basically, very similar to WiMAX, we divide the time into what we call multi-frame, 120 millisecond multi-frames. So this is the multi-frame number 1. So this is okay. So we divide into multi-frame number 0, 1, 2, 3, all the way up to 25. So this is in time domain, by the way. All right. So this is just one carrier. All right. In frequency domain, you can imagine there are 400 carriers, which we are not showing here. So just one carrier divided into time. Each multi-frame is 120 millisecond long and is divided into 26 frames. So each frame is 120 by 26 millisecond. So there is a we call it a TDMA burst. So there is a burst, and so on and so forth. You can call them TDMA frame. And each burst has basically these many bits, so there are first 3 bits is called tail bits. The next 57 bits are data bits. 1 bit is stealing bit, and we'll explain that in a minute. Then there is a training sequence of 26, 1 bit of stealing, 157 data bits, tail bits, and so on and so forth. And there is a guard bit, means empty period for 8.25 bits. So each burst is okay, all right. So basically, this is not a burst. This is a frame, and each frame has 8 bursts. All right. So each burst is 15 divided by 26 millisecond long. Each frame is 120 by 26, and each burst is 1/8 of that, 15 by 26. It's long. Okay. So the mathematics is shown in this example here. We are going to go through the whole example. So let's say we have 890 to 915 megahertz uplink and 935 to 960 megahertz downlink. So basically we have 25 megahertz. That is divided into 200 kilohertz channel. So 124 of them we get, because they are 25 megahertz, and we have divided by 200, we get 124 there. Now each channel is TDMA with a slot period of 15 by 126. So 8 burst period make a TDMA frame of 120. One channel is 1 burst period per TDMA frame, and so 26 TDMA frame is 1 multi-frame. So we saw that 26 frame is 1 multi-frame. Out of those, 24 are used for traffic, 1 for use for control, and 1 is left unused. And so there is this thing called slow associated control channel, SACCH, right in the middle here, SACCH. So this number 12 frame is reserved not for the user but for control, and that is called SACCS. So whatever control has to be sent is sent through that during that time. So there is SACCH, and if one channel is not enough, then we can use half of the bits from the other burst. So basically what we can do is we can stealing bits from the other burst. So this is a whole burst, and we can steal half of it, right, for control. So the user can still be talking on this part, but half of his bits has been used up for control, and that is indicated by putting this stealing bits. That indicates that this is a control bit. These are control bits, not the data bits. Okay, so that's what the stealing is all about. So that is slow, and this is fast, and it is fast because this can happen. How often can you steal? How often can you steal? How big is the burst? 15 by 26 millisecond, right? Whereas this, how often can you send control channel here? Every 120 milliseconds. So this is slow and this is fast. If you need to, for two reasons you might want to steal. One is because you want to send something fast, and second thing that you don't have enough on the slow channel. Yeah.
What is 15 by 26 milliseconds? That you said 15 bits in 26 milliseconds?
No. 15 divided by 26 milliseconds. So that number comes out to be, I mean, I could have put 0.4 millisecond or something like that, 0.56, whatever number that comes out. So it's just a fraction.
Okay, what is the bits referred to?
And so given the number of bits per second or millisecond or microsecond, the total number of bits you can add up here, and that will come out to be, that must be on the next slide. Total number of bits is 156.25 bits. Okay, because they use this 270 for 8 slots and so on and so forth. Anyway, so the rate is so many bits per slot, and therefore after the encryption and everything else you get is 9.6 kilobits per user. And so basically the voice, normal telephone voice is 64 kilobits on the wired networks, and we compress it to 16 kilobits for the cell phone networks. So basically, you know, you need all the bits here, which is these many 100 basically 9.6 kilobits. So let's see, 1 minute, hold on, half slot. So if you get the whole slot, then you get the full cellular quality. If you get half slot, then you get 9.6, right? So this thing is full slot, 156 bits. But if you get only half of it, you get 9.6. Okay, so let's do the calculation. Okay, so the stealing bits identify whether the half slot has been data control, and then 200 kilohertz, and that is translated 270 kilobits. If you divide that by 8, you get 34 kilobits per slot, and so you get basically, if you multiply by the time, you get so many bits per slot, and that will give you twice 9.6, 156 per slot. So 270 divided by 8 is 34 kilobits, and half of that is 17, and that you get 9.6. But if you get the whole slot, then you get twice that amount. Okay, so this 9.6 is for the half of the slot, but for the full slot you can put your 16 kilobits of payload. So your payload is 16 kilobits. Okay.
How does the 0.25 bits work?
Why 0.25 bits?
Right. Because bit can be divided by 0.25.
Yeah, so there is no bit, actually that is period. So there is a guard period which is as long as 8.25 bits. It's just an empty period. All right. So more, basically SIM module is actually a computer. It's a microcontroller which has a computer and a storage, and it contains all the authentication, encryption, and accounting information. And you need a 4-digit PIN to activate the SIM card, and it can contain additional information. Okay, so now so the mobile sends identities of the 6 candidates base station, and the MSC selects the base station for use. Like we said, the MSC is the main brain behind deciding as to who connects to where. And then they also invented something called SMS. Now it is so common in the United States that I want to introduce to you. Short message service, text messaging services. And so basically what that is, that you can send up to 160 characters over the control channel. So basically what happens is, in the control channel you have many of these slots, and one slot is a certain number of slots are allocated so that you can send up to 160 bytes. 160 bytes is 160 characters without making a connection. So it's immediately sent, as opposed to when you make a phone call, you have to set up a connection, which takes few round trips. Right? So even today, when you do SMS, they are limited to 160 characters. Okay, and these SMS can be unicast or broadcast. All right, so let's just do a little bit more math. And listen carefully, because this is a small part of the math that we can give you some questions in the exam. And so I actually will design an exercise homework which is not there in this one, but they will put one once I design it. So let's just go through this example. Cluster size is 7. User density is 100 users per square kilometer. The frequency spectrum is 49 megahertz. Bit rate required is 10 kilobits for the uplink and 10 kilobits for the downlink. The modulation rate is 1 bits per hertz. So this is given. From this given information, we can calculate as follows. First of all, we are assuming FDMA, FDD. So FDMA is, what is FDMA? Frequency division multiple access, and FDD is duplexing. Okay, so what we are doing is we are going to use uplink and the downlink separate, right? And then we are going to, each uplink and downlink we are going to divide into channels, into carriers, and then we are going to do time division TDMA on the top of that. So okay. So the question is, how much is the bandwidth available per cell? How many users can be calculated? What is the area? And what is the cell radius assuming circular cells? Okay, so these are the questions. Second question is, if the available spectrum is divided into 35 channels, then answer all this. So let's just do the answer. So the first A, the answers are here. So use FDMA, TDMA. So basically we have 49 megahertz, 900 to 949 is 49 megahertz, and we are going to do 7, cluster size is 7. So each cell can only use 1/7 of that, right? So each cell will use 7 megahertz, and because we are going to do FDD, we are going to divide that into half. So each direction can use 3.5 megahertz. This is just an example, and basically it's like planning your cell service or something like that for the carrier. So that is the first answer. How much bandwidth per cell? First we divided how much, we found out how much is for the both directions, and then we divided how much is for each direction. Now we need how many users can we support? We need 10 kilobits for each user and we need 1 bits per hertz. If we use 1 bits per hertz and we need 10 kilobits, how many hertz we need? 10 kilohertz. So each user needs 10 kilohertz, and therefore given 3.5 megahertz, we can support 350 users. Okay. Now, so what is the cell area? So since there are 100 users per square kilometer and we can support 350 users, the cell should be 3.5 square kilometer, right? And then what is the cell radius? Since this is the area, we can calculate the radius. Pi r square is equal to 3.5, so r is 1.0056 kilometer. Okay. Any question about the calculations on this slide?
What does 10
Sorry.
kilobits per user mean? 10 kilohertz. Why is that?
Okay, yeah, why 10 kilohertz? Okay, so here thing. Each user needs 10 kilobits per second, that we know, right? And the modulation rate is 1 bits per hertz. So each bit is equal to 1 hertz.
But in reality, can that really happen?
right now, so that is an old example. Actually, today, I just mentioned earlier in the lecture, how many bits can we get today? 6. And next year maybe 12. I mean, the thing is, the number keeps going up. All right. Now, if the available spectrum is divided into 35 channels and TDMA is employed within each channel, what is the bandwidth and data rate of each channel? So, if there are 3.5 megahertz divided into 35 channels, each channel is 100 kilohertz, and the data rate is 100 kilobits. Now, how many slots are needed to make the number of users? Now, if you have 100 kilobits in each channel and you need 10 kilobits per user, then you can put only 10 users per channel, right? So, you need 10 slots. So, if TDMA frame is 10 millisecond long, how long is each slot? So, the TDMA frame is 10 millisecond long, so each slot would be 1/10 of that, 1 millisecond long. So, how many bits are transmitted in each time slot? So, if you have, this is the key, and many students make a mistake here, is that each slot is 1 millisecond long and rate in the slot is 100 kilobits. Even though the user's rate is 10 kilobit, what the user is doing is it's taking its bits and transmitting into 1/10 of the time. So, the average rate is 10 kilobits, but their instantaneous rate is 100 kilobits. So, each slot has 100 bits. So, this is the kind of calculation that the GSM designers must have done to come up with those numbers that we saw a minute ago. Right? This is obviously not GSM, this is just an example of how calculation is done in a system which has both TDMA and FDMA. So, for FDMA part, we divided that into channels here. So, this is the FDMA part. Each channel is divided into 35 frequency carriers, so base channels. So, we get 100 kilohertz, and then we divide into time, 10 time units, so we get 10 kilobits per user, user channel, if you want to call it, per user. And so basically, this is the kind of calculation that was done. Any question about this? All right, that brings us to the end of this module. And so the summary, 5 key points are: first, that now we understand this geometry of the cells. Cells are approximate circle, which means hexagonal actually, to be exact. And they are not really exact hexagonal, by the way. In the real world, they are much different shape, because when you deploy there are mountains and valleys and buildings and so on and so forth. So you really have to go around figuring out where the power is so low that the cell ends, period. So a cell could be really a very odd shape, and the next cell has to be designed so that it covers that area which is not covered by this cell. So, but approximately, if you assume that the whole world is flat and things like that, then you do this calculation which we saw, and which really require knowing the number n, the cluster size. Once we know the cluster size, then we can calculate the cell radius and the cluster radius and so on. Second thing we did was we understand 1G and 2G. I haven't talked about 3G, but since this slide says, I will mention this. The main difference between 1G, 2G and 3G is 1G and 2G were designed for voice. 3G is being designed for was designed for data. Right? So 1G was designed with analog voice and 2G was designed with digital voice. And because of digital voice, you can do a little bit of data as well, but that data rate is so low that people will really not use it. With 3G, the data rate is usable enough, right? Usable. Then an example of 1G is amps, and there was another name we had mentioned, and I don't know if anybody remembers, starting with T in Europe. What was the 1G system in Europe? TACS, TACS, right? And so both of them use FDMA, both of them use analog, and so on and so forth. Then we moved on to CDMA and TDMA, right? And so the TDMA is example is GSM, And the CDMA example is IS95A. Let me put A there because that's important. Okay, and we saw how GSM works. Basically what you do is you take your frequency, divide that into frequency channels, and each channel you divide into time slots, and then you could divide into lots of pieces, and then you give some piece to the user at the end. All right, in terms of much of this is described in these two books, which are both are on the reserve in the library, and then there is this paper, GSM Mobile Services. In addition, there is enough on the Wikipedia, actually 2 pages full. So if you do Wikipedia, I don't think you need to go to the library, but you need to do one or the other, either go to the library or go to the Wikipedia to read all about it. The homework is missing right now, but it would be very similar to the example that we just worked out, this example and the previous example. So I will design one and send to you by mail maybe, or maybe give out next time. I have to think about that. But you need to do this exercise by yourself with different numbers, so that you can do that in the exam as well. Okay. Any question about 1G and 2G? Yeah.
Sorry, what is due next Monday's project?
Okay. Hold on to that question. Any question about 1G, 2G?